Well, we've discussed magnetic forces on moving charges. Now let's consider current. Well, current is really moving charges, isn't it? So you're going to see there's a close tie, a close parallel here. So we have a segment of wire, drift velocity VD, length L, cross-sectional area A, current density J. Let's immerse that in a magnetic field. All right, well, the magnetic field, if you put your fingers in that direction, that'd be into the screen, and put your thumb in the direction of drift velocity and you'll see that the force is up, right? So, what is that force? Well, the force is QV cross B. Now the cross product in this case, we'll assume the direction of the charges in the magnetic field are perpendicular, so it'd be just QVDB. The charges are actually moving at this drift velocity, so it's got the same form there. Now let's readdress or re-examine N, number of charges per volume. Then Q, the amount of charge, is number of charges per volume times the charge times the volume, and the volume is cross-sectional area times L. So the force is NQAL VD times V. I can rearrange that just a little bit. We'll bring the VD in and we'll put the L out. All right, why am I doing that? Because number of charges per volume times charge times drift velocity turns out to be the current density. Current density times area is current. So F is equal to JA, which is current, LB, which is ILB. Now to be complete, ILB perpendicular, which is ILB sine of theta, and we have a new relationship for force, IL cross B. Look how similar that is to QV cross B. Current, charge. V, well, current is flow of charge, so the velocity is inherent in that. And length of that line of charge, you could say that's flowing, cross B. So very similar. Now just a little side note, if the conductor is not straight, which typically it's not, we've got wire curving around all over, differential force, IDL cross B. The vector is DL, not current. The current actually is not a vector because it's going all over the place. The direction keeps changing. It just follows the wire. So we're kind of thinking this in terms of a line integral that we've seen before. Now the DL is always in the direction of the current. The current is the direction of flow of positive charges. So it's not necessarily the drift velocity of the charges. The charges can be plus or minus. They can be positive or negative carriers. I'll readdress that when we talk about Hall effect. So that is our definition of force on a current or a current element. A little length of wire with charges flowing in it. Very useful. Okay, a little example here. We are going to consider a conductor of this strange configuration immersed in a magnetic field B coming out of the page. And we have current I flowing around here through the whole thing. This little straight line segment is of length cap L, and it's the curved part is radius R, semicircle. So the force along the straight line segment is IL cross B. So there's L, and the cross product is complete. It's completely crossed. They're perpendicular. So this is just ILB. There's the force. Now, what about the curved part? And by the way, I should clarify what direction that is. Fingers out of the page. And current. Get your fingers out of the page and put your thumb in the direction of current. It's this. Yeah, you're pointing your fingers at you with your hand turned upside down. But your palm points up. That's the important thing. Now let's look at this little element of the half circle. All right, so there's a differential angle here, d theta. and it's at angle theta. And its length is dl, differential length, which is r d theta. So the force on there should be in this direction. Fingers out of the page. Again, put your thumb in this direction, and the palm is going to be pointing radially outward. Puppy, what are you doing? You're bumping me in the leg. Are you hungry? You already ate. I even gave you some of my fish. So here, take your ball. Go, get it. All right. Oh, sorry. The dog's bothering me. Now, this is differential F, differential force, and it's IDLB. Okay, so we found all this. B is a constant here. There is the length. There is the current. So that's I r d theta B. Now, this dF has a fx as a x component, which is I r d theta B cosine of theta, and a y component, I r d theta B sine of theta. Well, let's consider the total x part of the force acting on this semicircle. You may guess what the situation is going to be, or maybe it's not real obvious. Well, let's IRB, that's constant, and then we're going to integrate d theta cosine of theta, or cosine of theta d theta, from 0 all the way to pi. When we do that, we get IRB sine of theta from 0 to pi, which is 0. Yes, symmetry. If you put this little force outward all around here, it all cancels. Okay, good. Now, what's the y force? IRB, integral 0 to pi is sine of theta d theta, negative IRB cosine of theta from 0 to pi, which is 2 IRB. So the total force is the force from the straight line segment, ILB, plus twice IRB. I'm sorry, first one, I think I said IRB. ILB plus 2 IRB. Oh, 2R. Yes, that's twice the radius. That's like the length of a straight line segment along here. In fact, that helps us understand that the entire force on this is the same as replacing that circular part with a straight line piece. So the total force is IB L plus 2R times the quantity L plus 2R, J, because it's in the positive y direction.